Okay, so welcome back to RandomMathsInc. I haven't posted in here for a really long time, and for a pretty good reason, because I've become very busy for some reason. It's a bad excuse, I know, but still. So basically, recently had to give a presentation, and I could choose any topic for that presentation, which was really cool. So I decided to do a presentation on something called the Second Law of Thermodynamics, and at first I didn't really want to make a video on it, but then afterwards, after making the whole presentation, I was like, actually, this is not a bad video to post on this channel, and I haven't posted for a while as well. So I thought maybe I would try to maybe put that on as a content for you guys. The only problem was that the professor filmed the whole presentation, but the audio wasn't so good. I'll give you an example of it right now.
Does everybody know what the second law of thermodynamics is? No. Then you must. Okay, so assuming that. Okay, so
as you can see, there's like the audio is a bit fuzzy and stuff, and so I decided that maybe I could try to refilm the whole thing. And so this is why I'm in front of my TV. For some reason, I have like a huge TV in my dorm. Don't ask me why. It wasn't my idea. But what we're going to be talking about today, as I said, is going to be talking about the second law of thermodynamics, and I'm basically going to be re-giving my presentation to you guys. So hopefully that's going to be fun. This is a different sort of video. I'm not sure if this is going to be a format that I always do. Probably not. But I just thought, this could be like a good experiment or something. So I'm going to be talking about the second law of thermodynamics, hopefully in around 10 minutes. Probably not. And so the first question I want to ask you guys is, what is the second law of thermodynamics? Well, there are many statements of second law of thermodynamics. If you have a good physics textbook or a good textbook on thermal physics, you can open up and you can read about it. It's like a whole list of definitions. The first one that you might have come across is saying things like heat transfer occurs spontaneously from high temperature area to a lower temperature area, which in a very broad sense, maybe a bit incorrect, is saying that if you have a higher energy place and a lower energy place, then the energy will tend to spread from the higher energy place and goes to the lower energy place if you don't do any work on it. That tends to be what nature does. There's also statements on entropy, saying that total entropy of a system can never decrease. That's also in a song by English rock band Muse. There's also the statements involving things like refrigerators or Carnot engines and stuff like that, which I really can't remember. And we know that the second law of thermodynamics is a pretty true statement. If I have a cup of hot coffee lying on the table, then the coffee will eventually get cooler and cooler over time, because the energy from the coffee is given out to the environment, which has got like a lower energy density, a lower temperature, in a very rough sense, right? So we know that second law of thermodynamics must be a true statement, but the question that we don't really know, or a lot of people don't really know, is why that must be the case. So that's what I want to try to answer today. What I'm going to be telling you, the argument that I'm going to be giving you, is based on a guy called Daniel Schroeder, who wrote a really good thermal physics textbook, and also has a paper pretty much on the why second law of thermodynamics must be true, and it's probably my favorite argument on why it must be true out of all the statements that I've seen. So this is what we're going to be doing today, right? Sorry about that. So here's what our journey is going to be like. I could really just go explain the second law of thermodynamics in a straightforward manner, but I'm not going to. We're going to take a little detour. We're going to do a bit of discrete maths, because after all, this is RandomMathsInc. So first, we're going to consider a math problem, which is going to seem a bit abstract, but just hang on with me. So this is the problem that we're going to be considering. Think of it as a mental problem if you want. So I suppose we have n indistinguishable balls, right? And think of it as ping pong balls, or just any old balls if you want. And suppose I have two rooms, which I'm going to label room A and room B. Now in either of these rooms, I'm going to have baskets. I'm going to have k baskets, which can hold an infinite number of balls. We're going to assume that's the case. And so the question I want to ask is, how many ways are there that I can rearrange the balls so that m of the balls end up in room A, and the rest of the balls, or n minus m balls, end up in room B? So now the question hopefully is pretty clear. I'm going to give you about 5 seconds to think about it. Okay, your 5 seconds are up. So let's consider the answers, right? So suppose I have m balls going into room A. So first I can find how many ways are there that I can arrange m balls into k baskets in room A. There is a pretty standard trick in discrete mathematics called sticks and stones method, which is a way of doing counting with pretty much like this exact setup. So what you can do is there's an entire proof on it, which I think I'll put in a separate video. Check the description. But the answer that you'll get out of this is that if you have m balls and you have k baskets, the number of ways you can rearrange the balls in this case will be m plus k minus 1 choose n. This bracket here is something called the choose function. It's like something that you can do in combinatorics, and that will be how many ways you can choose. You can rearrange the balls in the first room. I'm going to label this as omega a. Okay. Now I can do the same thing for the second room, for room B. And it turns out the equation that we get will be very similar. Instead we have n minus m balls, so the number of ways you can rearrange the balls in room B will be n minus m plus k minus 1 choose n minus m. As you can see, it's pretty much the same thing, but I'm replacing the m with n minus m because both of the rooms got k baskets. So there's a nice sort of symmetry going on there. This is how many ways you can rearrange the balls in room A. This is how many ways you can rearrange the balls in room B. And so if I want to find the total number of ways I can rearrange the balls, I can take these two numbers and multiply them with each other, right? And so I'll get this total sum here. So this is how many ways I can rearrange n balls so that m of them ends up here and the rest of them ends up here. So I'm going to call this thing the multiplicity of the system. Basically, if I have a certain number of balls in either of the rooms, how many ways are there? Can I rearrange those allocated balls in each of the room to go into each of the baskets that we have? That's basically what multiplicity is. Now, looking at the equation, just staring at it doesn't really make any sense. So what we really want to do is we want to plot the graphs out. So that's what we're going to do. So I plot the graph out. It's going to look something like this. This is for the case where we have 10 balls and we have 6 baskets in either of the rooms. As you can see, there's a couple of notable things right away. First of all, is that the graph is pretty symmetrical. There is a highest point in the graph, a very clear highest point, and it's right here, when m is 5, or right in the middle, when all of the balls are distributed evenly between the two rooms, which is sort of what we expect, or at least intuitively what we might expect. Right? There's very little ways to rearrange all the balls so that all the balls are just in one of the rooms and no balls in the other room, compared to evenly distributing balls between the two rooms. And it turns out that if I have more balls in more baskets, like for example having 100 balls in 50 baskets, the graph still centers at pretty much the same place, meaning that the highest multiplicity state will still be when the balls are distributed evenly between the two rooms. What changes now is that the graph is a lot more squished in, right? And so this becomes even more clear when I pump the numbers up even higher. Now we have n, the number of balls being 2,500 and 100 baskets in each of the rooms. As you can see, the graph is a lot more squished now when we have a higher n and a higher k. But the center is still pretty much in the same place, meaning now there's virtually 0 ways, if you want to think about it, of rearranging all the balls in one of the rooms, compared to having all the balls distributed evenly between the two rooms. Now there's another way we can think about this, this graph that we have. Suppose now that I have a ball, and this ball can go into either of the baskets in any of the rooms with equal probability. It can go into room A and go into any of the baskets, or it can go into room B and go into any of those baskets with equal probability. Then this graph, these two graphs in fact, will roughly be the shape of the probability of us seeing some number of balls in room A, right? So what this graph can roughly tell us is if any of the states, any of the individual configurations of the balls are equally likely, then we're super likely to see all the balls distributed about evenly between the two rooms. And the higher the number of balls we have, or higher number of baskets we have, the more we're likely to see all the balls distributed evenly between the two rooms. Here, when the number of balls and number of rooms are a bit smaller, we might be a bit likely to see like the edge cases, for example. But as n and k gets bigger, as there's more balls and there's more baskets, it's less and less likely for us to see all the balls being clumped into one side or being skewed over or something like that. So keep this idea, and now we're going to go back into physics, right? So what we can do is now, rather than thinking of the baskets as we had before, we're going to think of the baskets as atoms. Now, what I mean by atoms, well, these baskets right now are just baskets, right? The atoms are physical things, right? Now, these atoms, we can assume that they can be excited into like a higher energy state. And the way they do so is by absorbing some amounts of energy. And rather than going up at any amounts, they only go up in discrete steps, right? And so what we can do as well is we can now think of the balls that we have as these units of energy. And these units of energy, for example, 1 unit of energy can go into one atom and excite it by 1 level, for example, right? And so now the problem that we have is no longer just about baskets and balls, but now we have a problem that looks a bit different. So here's how I can reframe the entire problem. Now, suppose I have two materials, which I'll call material A and material B. And in either of these materials, we have some number of atoms, K atoms. So we have K atoms in room A, in material A, sorry, and K atoms in material B. Now, I have big N units of energy, and I want to distribute these units of energy into either of the rooms. The question is, how many ways are there that I can rearrange M units of energy to be in material A, and the rest of the energy units to be in material B? As you can see, this is pretty much the same problem, just worded very differently and a bit more confusingly, if you ask me. But because it's exactly the same problem, the answer will be exactly the same. Right, so we can use the exact same multiplicity, big omega, that we had before, which is just going to be the same expression that we have, which means that I can also use the same graphs that I've had before. So now we have the graphs of when we have n equals 100 and n equals 2500 as we had before, right? And so the graphs, again, so much of the explanations that I've had before, much of the analysis that we had before will apply in this case as well. The most probable state that we'll find is when energy is distributed evenly between the two sides, and more importantly is that as we have a high number of atoms and high number of energy, the most likely state that we're going to find will be more and more towards the middle. The graph will be a lot more squished. We're going to be less and less likely to find the energy being skewed over or just simply in one of the states, in one of the materials, rather than being spread out. And really, if we consider like real life materials outside, like for example in our examples, then what we really find is we're not just finding atoms, like 100 atoms in each material. You're finding large number of atoms in a material, in the order of, say, Avogadro's number, 10 to the 23 atoms in a material, which means that our graph doesn't really just look like this. It's going to be a lot more squished, maybe something like this. Right, this is a graph, a hypothetical graph for very large n's and very large k, or lots of atoms and lots of units of energy. The graphs become really, really sharp. So we're super likely to just find our energy being distributed evenly between the two materials, just right there in the middle, and virtually zero. Virtually, we're not going to ever find energy being skewed over in one of the sides, whatever. So if I have a unit of energy which can go into any of the atoms in either material A or material B with equal probability, they're allowed to move around to any of the atoms with equal probability, then the total energy that we're going to find most likely will be distributed very evenly between the two materials, as seen by this graph, which is really sharp. Now, this is where the fun part happens. Suppose now that I start somewhere here. I start with a state here, which represents a state where most of the energy is clustered first into one of the rooms, right? Sorry, in one of the materials. I keep getting the room and the material mixed up. So now suppose I have a state where the energy is clumped into one of the materials, meaning that material A has got all the energy units, for example, and hardly any energy units in the other material. Now suppose I walk away, I go away for a second, I have a cup of coffee, and these energy units are allowed to move around freely. So this unit of energy can go into any of the atoms in either materials, and the same for all the other units of energy, right? Now, because the units of energy are allowed to move randomly now, what I find is that when I come back, most likely the units of energy will have spread itself out evenly. Because if you go back to the graph that we remembered from before, the most probable state of the energy that we find will be a state where the energy is distributed evenly between the two sides. So if I start here and I let all the energy move around randomly, it can go to any of the atoms in any of the material, then most likely we're going to find a state where the energy is distributed evenly. And so, if I start here, if I start looking right here, looking at all the states where the energy comes into one of the material, I walk away, and I don't consider the atom's motions or anything for the energy of the atom's motions or anything for a second. And I come back and I see the state where all the energy is spread out evenly. This is like looking at all the energy first starting in material A, and then eventually just diffusing itself into material B. It's like the energy going from this here, sort of spreading itself out into material B, ending up with a state looking like this. So basically, we have two things going on. We have most likely state of the atom being a state where energy is spread out. And if I start with this state, with all the energy clumped into one side, the energy will also tend to move around and spread itself out so that the energy is evenly distributed between the two sides. So it almost looks like, from an outsider who doesn't know about the motions of the energy, that the energy is being spread from a high energy place to a low energy place. And this is basically just the second law of thermodynamics, as we sort of know that the energy tends to spread itself out from a higher energy place to a lower energy place. And so really what second law of thermodynamics can really be thought of is not just any like elaborate thing that happens due to like invisible forces, but just something that happens purely because the probability of it ending up in that state is just so much more likely. I mean, sure, probability dictates that all the energy might clump up in material A, or it might just transfer itself and then just all clump up in material B, for example. But the probability of those states happening is really, really low. It's so low that it's virtually never going to happen, and which is why we can take the energy spreading out evenly as a fact of nature, and in fact, as the second law of thermodynamics. So, second law of thermodynamics isn't really like an absolute law in a sense that like it must happen 100% of the time, but a really, really strong probability statement, so strong that virtually we're never going to see anything else, right? So that's the second law of thermodynamics, and there's one more thing that I want to talk about. Because really, multiplicity, as we've seen, is a bit harder to work with, right? Because it involves two numbers and two numbers multiplying with each other in our case, right? And the numbers of multiplicity can get really, really, really big. And so usually what we do is we use something called the natural log of multiplicity instead. And there's a couple of good reasons for it. One is when we take natural logs, the numbers become a lot smaller. And secondly, when we have a situation like we had, where we want to find the total multiplicity of two systems combined, when we have omega, we have the multiplicity, we had to multiply them together. But when we have the natural log of multiplicity, we're adding them together because logs add numbers, right? So this is a properties of log, and it makes it a lot more convenient for us to work with. But there's also one other reason, is because if I have a graph of multiplicity alone, and I plot the graph of the natural log of multiplicity, it turns out that the peak of the graph still remains pretty much at the same place, which is a nice property. So it turns out that when I have a graph like this, representing the multiplicity, the highest state will still be the highest state when we take the natural log of the multiplicity, right? And so it turns out that, for example, if I have a state like this, the most probable state will be the state where it's right in the middle. But in this case, it'll also be the state that's also right in the middle, which means that the most likely state, which has the highest multiplicity, will also have the highest natural log of multiplicity. the most likely states that we have will be states where natural log of multiplicity is the highest. And so because it's so nice, we can give it a little symbol, we can give it a little name, and we call this the entropy of a system. Basically, the entropy of a system, which we represent by the letter S for some reason, is equal to the natural log of multiplicity, right here, multiplied by something called Boltzmann's constant. Why do we have this Boltzmann's constant at the front here? I don't really know. Probably has something to do with units. I should really look this up before I made this video, but I guess that ship's has sailed past now, so I really can't do anything else about it. And so basically entropy is just equivalent, very equivalent to the multiplicity of a system. As you can and then you can see why the statement on entropy always increasing must sort of apply. If I start with a state which is really unlikely, a state of low multiplicity, then the state will tend to evolve to a state of a higher multiplicity, which means that it's like a state starting with a lower entropy going to a state of a higher entropy, because that's just what is likely to happen. And so this is sort of the second law of thermodynamics explained in terms of this quantity here called the entropy, which is pretty cool. And so to recap, we have the second law of thermodynamics, which can be stated in a couple of ways. In very rough sense, the first way you can state is by saying that the energy tends to spread itself out, and secondly by saying that the entropy of a system tends to increase. And either way you can look at the second law of thermodynamics, it's just a really strong probability statement about why something happens. Just because it's really likely, hence it happens. And basically that's the second law of thermodynamics, and that is statistical physics for babies. Thank you very much for watching this weird video from RandomMathsInc, and I guess I did say it was going to be 10 minutes. That was way longer than 10 minutes. I didn't know how I kept my actual presentation under 10 minutes. But yeah, I guess I'll see you guys sometime later. Yeah, bye. Oh, and by the way, I never really got to say thanks to us reaching 1,000 subs. I'm pretty sure we passed that at least like 4 or 5 months ago, and now we're heading towards many more subscribers. So if you're new here, thank you very much for joining in, I guess. And I promise I'll try to make more videos.